So today we're going to talk about acid-base buffer systems. This is probably one of the harder topics that you're going to see all year. So please, if you need to pause the video and really read over the slides and digest what I'm saying and replay it, you should definitely do that. So on the surface, if we look at an acid-base buffer system, it really is just an aqueous solution where the pH will remain pretty much stable even when you try to disturb it by adding, acid or base to the system. And this is really important in biology because in biology, systems need to maintain a pretty stable pH for the enzymes and the organisms to survive. So I give you two examples, lakes and blood. Hopefully there's not lakes of blood, but those are two pretty common examples used. Blood pH needs to be maintained in order for the enzymes to work, and lake pHs also need to be maintained for organisms to survive. So the buffer actually contains acids and bases within it. That's what allows it to actually maintain its stable pH. So the buffer must contain an acid component. The acid has to be weak, and the purpose of the acid component is so that it can react with hydroxide ions if we add them. You also need to have a basic component to react with the hydronium ions. And this will often be a weak base. A lot of times, they'll be conjugate pairs of each other. Now, it doesn't have to be a conjugate pair, but it oftentimes will be a conjugate pair. So let's go through and talk about how a buffer is actually going to work. So a buffer behaves the way it does because of something called the common ion effect. And what we're going to see is that we can actually get the buffer to shift away towards either the left or the right, depending on what we add to the buffer. And that's because we will have both an acid and a base component present that will allow the equilibrium to shift. So if I were to add, for example, here's my buffer system. If I were to add some acetate, this should have a negative sign. If I add some acetate, the acetate ion will react with the H3O+, and it will shift the reaction to the left. If I add some H3O+, some HCl, I can also shift the equilibrium left. If I add OH-, which I don't show you here, but if I add OH-, the OH- will actually react with the acetic acid component, and it will cause the reaction to produce more CH3COO-, and that will actually shift the reaction to the right. So we can get the reaction to shift back and forth, but the key is that if we add H3O+ here, so if we add H3O+, it has a component of the buffer to react with. It can react with the acetate ion. And if we add some OH-, it has a component of the buffer to react with. It can react with the acetic acid component. That is why a buffer needs both an acidic and a basic component. The idea behind that is so that this way the pH will stay constant. If the acid or base didn't have anything to react with, well, then we'd have a problem. We'd have a situation in which the pH would change drastically. But here, if we have a basic component, the acetate ion reacting with the H3O+, it'll absorb that H3O+. If we have an acidic component, like acetic acid, reacting with hydroxide, that'll absorb the hydroxide. Okay, so let's take a look here. This is a graphical of what's going on. So here's my buffer. In this case, they use a weak acid, HF, and its conjugate base, F-. And they show you, well, if I have OH- here, the OH- will react with the HF component. And it will use up some of that HF component, but it won't drastically change the pH because the OH- gets absorbed. If I add H+, the H+ again, it will react with the F- component, and it will produce HF. So that's what's going on with this particular reaction here. So let's actually look at how this would work with a problem. So So we can write a Ka for this. So we have our HF and our H2O, and it's producing H3O plus and F minus. And we're doing this based on a Ka that we have for HF. This just looks like a regular system here of an acid reacting with water. The difference is going to come with the fact that I have some F minus already added to the system. I can also take this Ka that I wrote here and I can rearrange it for H3O plus, because most commonly on the AP exam you're asked to find the H3O plus concentration. So let's look at what a simple buffer problem looks like. So they ask you to calculate the pH of a buffer. It contains 0.5 molar acetic acid, 0.5 molar sodium acetate. Notice that I only write one equation for this because I have a Ka value. I'm going to write an equation that's going to represent the acid and water dissociating. Now notice the difference here though. When I set up an ice table, instead of having 0.5 and then 0 and 0, I have 0.5, 0.5, and 0. This is because my buffer contains acid, a weak acid, and its conjugate base. Now I go through and there's 0 H3O plus, so I have a plus X here, plus X on the product side again, and minus X on the reactants. At my equilibrium I have 0.5 minus X, 0.5 plus X, and X. And I go ahead and I plug that into my Ka, and notice now what I've neglected in my Ka expression is the following. I've neglected the minus X and the plus X. And so it's very simple. The Ka, 1.8 times 10 to the negative fifth, is equal to 0.5 over 0.5 times X. The 0.5 over 0.5 is just 1. So the Ka is equal to H plus, H3O plus concentration. So the X is equal to 1.8 times 10 to the negative fifth. And if we take the negative log of that, we get a pH of 4.74. So this is the easy way to solve for pH of a buffer. It's not so much harder at this point. Where do things get complicated? It's when we add acid or base. That's when we're trying to disturb the buffer. And as we disturb the buffer, we see what happens. Now, here is a continuation of the problem before. It says, hey, you have 0.5 molar and 0.5 molar of the acetic acid and sodium acetate. Now you're going to add 0.02 moles of HCl to this 1 liter buffer. Now something very important. What I do is I have a super ice table. It's like my BASA ice table. I call it BASA ice because you have before addition, addition of H plus, a shift, and after addition. That's my BASA part. And then I have my ice part. Now when I'm doing BASA, what I do is I take the substances, and this is all in moles. With my ice, this is in molarity. And in this case, it doesn't matter because we're talking 1 liter, so you're not going to see a difference. But look at what happens. Before my addition, we start with 0.5 and 0.5. 0.5 moles, 0.5 moles. And we have no H3O plus. Now we're going to try and disturb our buffer. Our buffer is disturbed by adding 0.02 moles of H3O plus. What ends up happening is the system will absorb the H3O plus. The acetate ion will react with the H3O plus. So that gets subtracted from that side and added to the reactant side. After addition, we have 0.52 and 0.48 and 0. Now I can take those numbers, put them back into molarity. In this case, they're the same because it was in 1 liter. And I have 0.52 and 0.48. And now when I do this, I can do my ice table. So I'm going to have my minus X, and plus X, 0.52 minus X, 0.48 plus X, and X. And then I'm going to go ahead and put that into my Ka expression. Again, I can get rid of the plus X and the minus X. I'm going to have my expression here. I'm going to solve for X, and then I'm going to find the pH, and the pH is going to be 4.71. Look at the change. It went from 4.74 up here to 4.71. Yes, the pH went down, but even when the pH goes down, that doesn't necessarily mean that there's a huge change. To show you that, imagine if I were to have just pure water over here. So if I were to have pure water, and I were to have 0.02 moles per liter, If you try to find the pH of that solution, the pH would be close to 2. So sorry about that, the bell rang, so I had to relocate. But if we were to take the 0.02 moles of that HCl per liter and put it into pure water, the pH of pure water, it would have started at a pH of 7, and then it would have actually dropped to something close to about 2. That's 100,000 change fold in pH if I did not have a buffer. The fact that I had a buffer and I had this basic part of the buffer that was able to react with the acid that I added, the pH changed from 4.74 to 4.71. And that is not a big change considering how much acid I added. Now what would happen if I were to take this same buffer and I were to add base to it? And this problem's a little bit more complicated. And the first thing that you'll notice is that I had to write a new reaction. And I had to write a new reaction because if we look back at this slide here, there's no OH minus that's in the reaction. Now we know from the slide up above here that the base is going to react with the acidic component. So the base is going to react with the acid. And so we can see that we can write an equation for that. We have the acetic acid reacting with the OH minus. We wrote a new equation that forms acetate ion and H2O. And this gets a little bit complicated because, again, I'm going to have my BASA table down here, BASA. It's going to be in moles. Notice what I include in that. I include the acid, the base that reacted with it, and the conjugate base that forms. Again, we're starting with 0.5 and 0.5. We add the OH minus, the 0.02 moles of it, and then that 0.02 moles, it gets absorbed. It reacts with the acid. It forms more of the conjugate base, the acetate ion. So in the end, I have 0.48 of the acid and 0.52 of the conjugate base. Now, what's a little bit annoying about this is that I then have to go back and use the original equation for the Ka. And so that's what I do here. I have my acid produces H3O plus and acetate. I have my numbers from the last line of the BASA table. And then I have my plus x and minus x. I plug it into my Ka. I solve for x. And I get my H3O plus. And I do the negative log and I get my new pH. So again, look at the pH. It went up a little bit. It went up to 4.77. But that was only a tiny little bit. Again, just to look at this, if I had 0.02 moles of NaOH, the pH of water would go from 7 up to a little bit over 12. That is, again, 100,000-fold change in pH if there's no buffer there. This is why buffers are so important to biological systems. The idea that the buffer protects the pH of places where organisms live or parts of their bodies that, like blood or cells, the pH, if it maintains this constant number, then the enzymes can work properly and you won't have some severe toxicity from either too much acid or too much base. So the last part that I want to show you for buffers is a little shortcut. Wouldn't it be so nice if I could just take this line here from the BASA table, right here and right here, these amounts, and just find the pH right from that? That would be amazing, right? If I could do that, and I didn't have to do a new ice table. And you're probably saying to yourself, well, how does he do this? And the answer is through the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation, all it does is it takes the Ka expression and it rearranges it so that we solve for H3O plus, and then I take the negative log of everything. The negative log of the H3O plus is pH. The negative log of the Ka is called pKa, and what I do is the negative log of HA over A minus, I make it positive log, that becomes A minus over HA. This is the Henderson-Hasselbalch equation. I'm going to highlight it here in purple. You should know this. It will save you so much time. Imagine if I tried to do this for my reaction up above. all I would have to do is plug in my numbers from that addition table. I wouldn't have to make a new ice table, and I could solve right away for the pH, which is what they normally ask for. Also notice that for the Henderson-Hasselbalch equation, I don't need to change it back to molarity. I can just very simply keep it in moles, and if I keep it in moles, then I can plug it right into the Henderson-Hasselbalch equation and solve. So we'll practice all of this stuff. We're going to practice a ton of buffers and do things. And here's one for you to try and bring in tomorrow. And let's look at this tomorrow together using the Henderson-Hasselbalch. If you want to torture yourselves and use the ice table setups, then go ahead. I mean, you could do extra work all day long. That's fine. But the Henderson-Hasselbalch equation, it will save you a lot of time. All right, thanks so much for watching, and we'll talk about this tomorrow.